Hello, my name is Luke Nelson, and my midterm project is over airfoils. So we use airfoils all the time. We see them every day in airplanes, uh, with the air rolling over the wings to create lift. Cars use them to help increase the aerodynamics to help with the fuel economy and the top speed. The windmills use airfoils for the blades and how they move with the in the wind. Birds use them to create lift to be able to fly, and propellers we see them used in boats to create propulsion to help a boat move. So some of the terminology we're going to go over is that the chord line, which refers to a straight line intersecting the trailing edge and the leading edge of the airfoil. The chord dimension is the dimension of the chord line. The mean camber line is a running line that runs halfway between the upper and lower surfaces of the airfoil. The camber line has a lot to do with the aerodynamics of an airfoil and will determine how much lift and drag you will have. So the leading edge is the outermost point of the airfoil. The trailing edge is the back edge of the airfoil. The angle of attack is the angle between the relative wind and the chord line. And then the angle of incident is the angle between the chord line of the blade and the rotor of, which usually refers to like a blade pitch angle. So then for drag, there are two different types of stress that has to do with drag. They are the normal stress and the wall shear stress. So the normal stress has to do with the pressure from the fluid distributing across the cross sectional area, while the wall shear stress is the relative roughness of the material. So you will have different roughnesses of material depending on what material you pick. Some will be smoother and some will be rougher. And then factors of drag are the velocity, viscosity, compressibility of the air, and then the drag also depends on the area, shape, angle of attack. And we normally use a wind tunnel to find the drag. And using the drag equation, we can rearrange it to find the drag coefficient once we find the drag in the wind tunnel. So the drag equation is D is equal to 1/2 rho U squared ACD, where D is the drag force, rho is the density of air, U is the velocity of air, A is the reference area, and CD is the drag coefficient. So for lift, we also have a lot of the same components as the drag. So with lift, that it has to do with air density, velocity, viscosity, and the compressibility of the air, and then also the surface area, shape, angle of attack also play major roles in the lift of an airfoil, which we usually comprise the shape, angle of attack, viscosity, and compressibility in a single variable called the lift coefficient, which you can find in the lift equation, which is L is equal to 1/2 rho U squared SCL, where L is the lift force, rho is the density of air, U is the relative velocity of air, S is the area of the airfoil, CL is the lift coefficient. So the pressure coefficient, it is defined as the CP is equal to P initial minus P infinity divided by 1/2 rho U squared. And then the lift coefficient we use as, it starts off with F lift is equal to FL, and then you can take the double integration over the surface. And then once you simplify it down, you end up with CL is equal to FL divided by 1/2 rho U squared A, where CL is the coefficient of the lift, FL is the force of the lift, and then rho is the density, U is the velocity, and A is the area. So the drag coefficient, it's unitless, and then it you really want a lower drag coefficient, so which you can lower by the skin fraction and the dynamic drag. And then you also have lift drag, which in like hydrofoils helps lift up an object, and hydrofoils lift up out of the water to give you lift. And then the drag coefficient is given by CD is equal to FD over 1/2 rho U squared A, where CD is the coefficient of drag, FD is the force drag, and then rho is the density, U is the velocity, and A is the area, which the area of drag depends on where you're looking at. You can have many different cross sections. And then in ANSYS, whenever we put it in, we can change the different sizes and boundary conditions, and then we can find the velocity, pressure, and many other parameters. And you can see in the graphs and stuff where the pressure coefficient is at its max, and then you can see how the velocities differ between the top and the lower, and I will show you a couple of examples. So you can see the pressure at -5 degrees on an airfoil, how it's got a strong high pressure at the top and a little low pressure at the bottom. At 15 degrees, you can really see how much the high pressure on the bottom and the low pressure on top. But at 0 degrees, you can see how it has a high pressure at the leading edge and then a low pressure on the back. And then at 10 degrees, it's like the high pressure moves down and the low pressure also moves up on the airfoil. And then at 10 degrees, you can see a whole lot of high pressure on the bottom and low pressure on the top. At 20 degrees, you can really exaggerate it and see all the high pressure on the bottom. And then here is a YouTube video dealing with the velocity of and how it changes with the pitch. So as you can see, flat, and then as we raise it up, you get this high velocity and low velocity down here. And then out here, you can see a real turbulent velocities going on out here to raise the drag coefficient. And then do this to the front. Okay, sorry about that. Here is the references I used in the project, and I would like to thank you for watching and hope you have a good day.